Good. Okay. Hey, good evening, everyone, and welcome to reInvent 2024. I'm super excited to be here on the stage to present today's topic, that is AWS IoT for Edge LLM deployment and execution. I'm going to introduce myself. My name is Nikit Pednikar. I am the Principal Product Manager for AWS IoT and Automotive Lead. Today, I am going to be sharing this stage with expert panels. It's Stefano, who is going to be the AWS tech leader for software-defined vehicles. And we have a special speaker from our customer team, Aptiv, who is Joey, who is the head of partner engineering and enablement. Before we jump into the topic, I want to set the stage over here, run you through the agenda that we'll be covering in next hour. It's going to be looking into the industry trends, the benefits and challenges of Edge LLM deployment, and how AWS helps in value proposition across the verticals. Then we will focus into the next piece of the section, which is going to be the modernization of the automotive architecture and how Aptiv is driving the evolution of the vehicle architecture over here. And finally, we are going to wrap up the session with the most exciting part, that is going to be the AWS reference architecture for the automotive use case and a demo that will show how these technologies come into real life. I like to start with a fun fact, and I call it a fun fact because what seems unbelievable when a new technology is introduced to us becomes a part of our life. Right? Let me run you through an example. Say you're coming home from your office and it's a scorching summer day and you open the door and you are invited with the heat wave. The next logical thing you do is going to set the thermostat. In my case, the thermostat is between my garage door and the living room. And imagine if you are living in a multi-story apartment or a multi-story home. It's a mini workout just to go up and down the stairs to do what? To change the temperature by a few degrees. Now let's fast forward the technology. We have so many technological advances like smart thermostats, we have voice controls, and even automated climate control. Right? That is what exactly technology is doing to us. It is bringing us effortless solutions that can adapt and give us real-time insights. Okay. I'm going to run you through some of the industry trends over here. The Edge AI ecosystem markets are expected to grow to 38 billion by end of 2026. And what are the key factors that are driving this edge adoption is going to be the ecosystem. Now, ecosystem consists of diverse players, right? Chipset suppliers who are trying to improve the power efficiency so that their chipsets are ready for the future of the AI. There are hardware OEMs who are standardizing their hardware so that it can work with the environment, as well as incorporating the technologies of open source so that it can help in scaling and simplification. Now next comes are the system integrators. They bring a lot of in-depth technology expertise which help companies maneuver through the complexities of Edge AI adoption. Then we look at the software service providers and the turnkey providers who are developing robust tools for the deployments of these frameworks. And finally, our cloud service AWS, who are strengthening the edge to cloud portfolios. Now, while most of the AI workloads today reside in the cloud, we are seeing an acceleration of the Edge AI adoption. And that is mainly driven by the combination of factors like connectivity, data governance, data privacy, and the demand for low latency. The third vertical is going to be the verticalization. Some of the verticals that are driving the Edge AI adoption are smart home, retail, manufacturing, automotive, and healthcare. Now, the last approach is going to be the technological approach. The classic question to build or to buy, right? If you are going to build your own device solutions, it's resource intensive, right? Both in terms of technology as well as the resource required to build it. The second is going to be buying a turnkey solution from the SaaS service providers. While most of the companies go for it, it helps in simplifying, scaling, and not reinventing the wheel. But a combination gives you best of the both. A combination gives you the flexibility of the open source technology and the robustness of the proprietary technologies. Now this slide, I want to answer the why behind the growing importance of the LLMs. Let's look at these 5 bullet points over here. Let's start with reducing latency. For LLMs, reducing latency is super important because you are processing the data very closer to the source. That helps you minimize the delays. Let's take the example of our voice assistant again. What is if you are having a conversation with a voice assistant and if there are delays, it disrupts your conversation and it's not very pleasant user experience, right? Edge processing does what? It helps you faster and real-time interaction with your technology. The second one is going to be bandwidth efficiency. LLMs help you in ensuring the bandwidth efficiency because not all data needs to go to the cloud. It's not only cost effective, but it's also important for battery operated devices. Think of IoT sensors or wearables, right? Now, with the edge processing, like we can do, the third point is going to be enhanced privacy and security. With LLMs processing the data as the edge, the sensitive data stays at the edge, right? This helps in improving the privacy and minimizing the security risk. Let's take example of some of the verticals where there is personalized data that is being handled, right? If it is healthcare or finance, you want the minimum data to be transferred so that there are no data breaches that happen. Now let's look at improved reliability. Your edge devices needs to function even if it is intermittent or no connectivity, whether it is an automotive vertical or a point of sales. Your critical applications need to function even if there is outages. And finally, the customization and personalization. It's very important for LLMs that they bring in customization and personalizations. If we take the example of the voice assistant again, and if I'm telling my voice assistant to play my playlist, right? I don't want to listen to my kids' playlist, right? So that's very important that because of the real-time operations and the data being closer to the device, it can give you personalizations in real time. Now that we have looked at so many benefits of the edge LLM processing, I want to run you through the challenges that we see, right, while processing the edge. Let's talk about the challenge of system integration and interoperability. Deploying LLMs and integrating with the edge, it's technically very challenging. And the challenges are amplified because of the number of the diverse devices, systems, and the platforms that need to work together. Performance optimization, reducing the latency and making sure the model is accurate at the edge is a delicate balance. So it needs to be, and it's amplified when you work with the devices which are battery operated, which requires optimization of the energy, right? As I gave the example of the wearables and the IoT sensors. Let's look at scalability, right? Scaling the edge deployments is resource intensive and it requires a lot of infrastructure investment. Model deployment and updates is also logistically challenging when you are deploying these models to a fleet of devices. All the more, if you look at the edge models when they are deployed, they kind of become static, right? So you need to retrain them so that they are kind of updated based on the real world changes and they are retrained constantly. We call it the big loop. And finally, data privacy and security is a big challenge. Because you are handling sensitive data at the edge, it needs to be secured, right? You don't want your personal or the business data that needs to be mishandled over here. Now I can map all the AWS services across these challenges, but that's not the goal over here, right? How I want to showcase how AWS is going to overcome these challenges is looking at the big loop architecture over here. If you look at the architecture over here, I want to divide it into 4 pieces, right? The AWS value at the edge, the control and the data plane value that it brings, the cloud integration value that you see over here, and finally, the security and privacy value that AWS adds. Now let's look at the edge. AWS has a number of partner integrations, and what it does is provides you tools and connectors. Now AWS Edge IoT services like AWS Greengrass and AWS IoT Core, what it does is helps you develop, deploy, manage and monitor your edge deployments very close to the device so that it can perform optimally and reduce the delays in real time. The second AWS value is on the control and data plane. The data is not only about integration, transformation, or organization, but what control and data plane services provided by the AWS make sure that your data pipelines function optimally. Now, coming up to the cloud integration piece, there are a bunch of AWS services like your serverless computing, network solutions, and storage services that help you connect your cloud integration with the on-prem devices. Thus, the overall value that we are showing over here is in the big loop, and security is top of the mind. AWS has a bunch of services that helps in data privacy and security. Now that we have looked at how AWS has the value proposition over here, what I need to give is some real-life examples of the edge LLM adoption. Let's start, and I'm not going to cover all of them, but I want to cover the exciting ones over here, right? Let's look at the first one, right? Our voice assistant. LLMs are enhancing the voice assistant because it can give you tailored, personalized inputs as well as real-time insights. It can even enhance your home security. The camera feeds that you get can look at the real-time feeds and provide you anything with respect to the theft detection. And finally, the smart kitchen appliances. I was very intrigued by it because it can give you real-time recommendations on cooking instructions, or even it can guide you through the available ingredients and tell you what needs to be cooked, right? So it's kind of interesting. The second one is the retail ones. It can enhance your checkout process and even streamline it by giving you real-time fraud detection, right? Somebody is not using the correct card, it may give you intimation saying that, hey, there is going to be some fraud that is detected over here in real time. And it can even help you with inventory management so that you can look at your shelves and plan your inventories so that your shelves are never empty. Going into manufacturing, right? The quality control. If you look at how LLMs can integrate with the quality control, it can look at the defects in the production lines in real time and even provide data insights on managing your production lines. Even for robotics and automation, it can give you some real-time insights so that the robots are working in harmony with your human workforce. Now coming up to healthcare, there are a bunch of clinical data that can improve with the LLMs at the edge, but the one that intrigued me was the emergency response. It can help your emergency response attendants to give you real-time data, and they can manage the patients accordingly. And finally, the automotive, right? I want to cover all of them over here because we are going to deep dive into the automotive use case later, right? LLMs at the edge can enhance your ADAS systems, real-time object detection, lane keep assist, and more. The second is in-car voice assistant, right? If I'm sitting in a car and if I'm telling, hey, play my music or make my seat arrangements as per the driver, it should understand that, hey, who is the driver, and it can make the arrangements accordingly. The third one is predictive maintenance. LLMs running at the edge can look at the health of the vehicle and predict the driver if there are going to be any issues in future. And finally, smart navigation. We were planning to have the demo on smart navigation, but we kind of pivoted a bit. But smart navigation is an important one, even with the EV adoption, right? It can help you plan your trips. It can help you route or guide even in an offline fashion or no connectivity at all, right? So these are some of the real-life use cases that can be enhanced with Edge LLM vertical approach. Now I want to introduce Joey over here, and he's going to take you to the next part of the presentation.
Thank you. Oh, we updated the title. Great. So my name's Joey Lorick. I am head of partner enablement and engineering at Aptiv, more specifically at our software business within Aptiv. Longtime software developer. I spent a long time in the IoT space building out connected systems, more than a decade helping customers design solutions like this. I'd say I've probably done it wrong in every way possible, but that's led me on a path on how to really do it right. I came to Aptiv about 2 years ago to focus on our partner co-build solution. Previously, I was at Microsoft leading our IoT platform there. And I'm really excited for some of the things that we can share today because I think that there's a really big shift into AI and ML at the edge, specifically large language models. And there's a lot of really specific details that have provided challenges in this ecosystem that I think we have some great workarounds for, some great solutions for. Before I move forward, if you don't know Aptiv, Aptiv's mission is to provide a smarter, greener, safer, and more connected future of mobility. Primarily, that's through working with large automotive OEMs. So delivering ADAS systems for improved safety, literally saving people's lives, electrification as we see moves to electric drivetrains, all kinds of things like that, and then connectivity, so intelligent connectivity to the cloud, to vehicles, other vehicles, to stoplights, all kinds of different ways that we can use connectivity in these spaces. And these are all systems that generate lots of data and have a lot of use cases where we can take that and talk to it, have interest in models, have things that we turn on that data. And our approach is really around mission critical industries. So Aptiv software business is Wind River Systems. Wind River Systems, our motto there is, if it matters, it runs on Wind River. We are underlying, I would say, almost everything that you don't think about. So if you flew here today, if you flew here to get to reInvent, it ran on Wind River. The power that's powering all these lights comes from a power plant not that far from here, big hydroelectric plant, runs on Wind River. Mission critical ecosystems across way more than just the automotive space that Aptiv primarily focuses on. Big focus on aerospace and defense, so like I mentioned, planes, healthcare, industrial, manufacturing, all over the place. And that puts us in a really unique position to say, how do we take some of these really modern technologies that are super, super cool, that are bringing all kinds of crazy productivity increases, great user experience improvements, to an industry that is literally life or death for a lot of people, highly regulated, highly bespoke ecosystems, especially in the automotive space. That's a big challenge. So I want to talk first about what does an edge device look like? If we take the requirements for some kind of system that we work with pretty commonly, say a couple hundred different user requirements, life or death on some of these, where, say the engine goes out, the brakes go out, wings don't have flaps come up, big challenges, absolutely no room for error. But we need to have all these different features and we want to look at the idea of bringing LLMs into the space. What do we do? So oftentimes we start thinking about separation of concerns. And we can think through this in a lot of modern software developer practices. So say I have 3 services, maybe I connect them with a message bus, I've got event-driven messages going back and forth. Services can operate independently, that's great. We have a lot of things to do. We can't just have it as a monolith. So we've got all these supporting services that we may build out. These all have to be connected. We're starting to build dependencies. This is starting to look like a microservices graph. There's probably a dozen different sessions that you can go on in this space in just the next couple days. But each of these have their own sets of needs, their own sets of communication that they need to have. Suddenly we have this architecture that has tons of dependencies, really complex, something that reflects a lot of what a modern cloud solution might look like. So what's the right way to go deploy this? You might think, hey, containers and Kubernetes and all this kind of cool stuff. What if I said we're going to take all these and we're going to build an individual bespoke piece of hardware for every single one of these services? We're going to put it on a 6-foot by 10-foot room, and then we're going to connect all of it physically with copper. We're going to have more than a mile of cabling across all this. Is that a good way to do it? I would say no. Actually, the answer for most of you would be that's insane. But actually, almost every person in this room has invested many tens of thousands of dollars to do exactly that. Because that is a car, or at least what cars were for a very long time. And I share this because there's some really good news of what's been happening in the automotive industry that leads to enablement of things like large language models at the edge. Compute is getting cheaper and more powerful. And that's enabling us to take what looks like a distributed system, and really is, and start to apply patterns and practices that we've seen in the software space for a long time. So looking at things like domain-driven design to say, how do we bring services together on commodity hardware that maybe uses things like a hypervisor to be able to take multiple sets of services that used to be individual chips and run them on top of something that is more efficient, more reusable, be able to get better power, sometimes higher reliability. This is a transformation that the automotive industry is going through, and it's something that is enabling all sorts of new capabilities. So I want to talk through a little bit about the history of the car, or at least history of software in the car and electronic systems in the car. If we go back quite a ways, we've got the functional setup, kind of the distribution that was here before, over 100 ECUs in the average car. This is a challenge. It certainly works, but it's a challenge because if I'm missing a chip, now all of a sudden I can't produce my vehicle. This actually happened in 2020, 2021. There were cars that couldn't finish the production line because the chip for the seat heater wasn't there. Well, I've got the other 99, I'm missing one, I can't sell that product, or I have to sell it with less features. Huge problem for business. It also means I have lots of bespoke designs, which can be a lot of challenge. We've been moving over the last 10 years or so to a more of a domain-driven model. So can I take some of these pieces and consolidate them onto a little bit more powerful hardware, and then use things like hypervisors to separate out the workloads so that I can say, hey, I've got 4 cores, this core does this one does this does this, this does this. We safety certify the ones that are needed, we move forward with the others. This has continued to grow. Over the last couple of years, we're seeing more of a zonal architecture, so further simplification of the hardware within a vehicle. This has a lot of things that are maybe things that you wouldn't even think about, like being able to take what used to be a mile or several miles of cabling within a car. Copper is kind of expensive. Being able to reduce that to hundreds of feet of cable, move it to fiber optics, move it to all kinds of other things, can greatly reduce things from a cost perspective, but it also greatly reduces things from a development perspective, because now I've got reuse. I have commodity tools that are starting to crop up. I'm looking at using CPUs that might fit in a desktop or a laptop, or in an industrial PC, things that are really common, and the software is becoming what's the difference. And that's really where the vision of the future is, and something that Aptiv has been focused quite a bit on, is the software-defined vehicle. So the concept of a software-defined vehicle is most of the architecture for the vehicle is actually defined in software services. We're using hypervisors, we're using containers, we're using modern tools and technologies to go develop what a vehicle looks like, alongside with some of the real-time components that might be separated out by a hypervisor. And that enables us to do some really cool things, because as we're starting to move compute together, the compute of 100 small little individual chips, when I go get an off-the-shelf processor, I'm not, if I have 10 100 megahertz chips, and all of a sudden I go get a 4 gigahertz processor to go do the same thing, I actually have a lot more power available. And that's enabling us to have things like really robust in-vehicle infotainment. So you get in beautiful screens, all kinds of graphics going on, connectivity, automated driver assistance, so safety features. Cars have gotten so much safer over the last few years. V2X, which is vehicle to everything. My car being able to talk to the stoplight to know when it's going to change, to be able to make wise decisions based on input from that, or maybe the security camera down the street, or maybe the car next to it. And AI and ML, so things like large language models running on the edge. If it wasn't for this kind of consolidation, we wouldn't see the horsepower invested in vehicles, and we wouldn't see the effectiveness to be able to go do these kinds of things and do them in a way where they're actually running on the edge. So not sending messages out to the cloud, but actually getting answers in the car where we need them, because we don't always have connectivity. So how do we actually go do this? So Aptiv has been working to standardize within vehicles on a product from Wind River called eLxr for Linux distributions in the automotive space. And I say distributions because it's a little bit different than how we used to do it. If I think of large language models, I think of containers. That's the first thing. How am I going to go distribute this? Probably some kind of container I'm going to push to the edge that's got an API on top of my model that's been trained in the cloud. That's not how we did Linux in the history of the automotive space. When I look at lots of small bespoke chips, really low power, typically we're building this from source. I'm using a tool like Yocto or Wind River Linux, which is a supported version of Yocto that we have, to go compile all my binaries from scratch, to compile the kernel from scratch, figure out what hardware support looks like, figure out all the security profiles that I need to have, how am I going to manage performance at the edge, what do I need to tune, thousands of kernel parameters I can tweak. It's actually a really complicated process. And I have to say, even culturally, the overlap, if I were to draw a Venn diagram of people that are building large language models and people that are compiling their operating system from source, it's probably me and maybe a couple other people here, but it's really not that big. And that introduces a challenge in of itself, because if I now expect a diverse team to be going and building this, now I've got somebody whose responsibility may have been, I write Python, I'm a data scientist, I want to test this out, here, go compile your operating system from source. That's a huge time sink, and that's actually a security risk, because our expertise doesn't necessarily overlap. We have to guard for a lot of that. And so what we're starting to see is a move towards Linux distributions. Linux distros have been out for a long time. Certainly there's plenty that are there, but finding one that is really designed from a mission critical edge AI ML use case has been challenging. And so we decided, hey, let's take the best and brightest of what we can find in the community and let's expand on it. So eLxr is building from Debian. So it's a Debian derivative. All your Debian applications will run as expected, but we've taken it, we've stripped it down, we've hardened it, we've leveraged our deep experience with hardware relationships, because that's our primary focus, is on the hardware space from our company, and use those to say, can we provide a single software supply chain to be able to deliver you your drivers through our ecosystem, your containers, your cloud native tools, your packages, things like AWS IoT services, so that you have one single place to go trust to be able to easily build something that has a low or small security footprint, makes it so that the time to market out the door is a lot faster, where I'm not as worried about somebody picking this up, throwing their model at it and saying, yeah, this is pretty good. Greatly reduces the amount of effort that we need to get things out the door. So reduce cost, reduce risk, reduce time to market by leaning on a collection of our best and brightest at Wind River and at Aptiv to put this together. Certainly not something only designed for the automotive space, but something that we have been working on in the automotive space quite a bit. This is actually available today. You can go to eLxr.org, so eLxr.org, and download it. It's a Linux distribution, so it's open source. All the sources on GitLab. You can come contribute with us. You can come work with us. We're happy to include more and more partners. It's a rapidly growing ecosystem. We announced this June? Yeah, sorry. Lexi's here. She's our product manager for eLxr. Really great adoption. It's been really fun to get to see this. It's really helping simplify what was a really challenging problem for us. So what does the developer journey for this look like? Of course, we're going to start with eLxr. This may be on bare metal in some use cases. We might deploy it right on top of hardware. Certainly in development environments we would. In a car, I mentioned hypervisors are really important. The idea of separating out, we were just having this conversation, separating out safety critical workloads from things like cloud connectivity, which may not have a life or death component. There's a very robust safety certification process that has to happen. We still think that those generally apply in real-time operating systems like VxWorks, but we can use the other cores to say, hey, let's run eLxr, let's do IoT connectivity, let's pull LLMs down. But on top of this, we have a lot that we need to manage. So fleet management is a huge challenge. Trying to build a couple things that are connected, a couple thousand things that are connected, not that bad. Trying to go build 10 million things are connected, it's a massively different scale problem, but a problem that AWS has had solved and solved for a long time. So there's a mention of Greengrass earlier. AWS Greengrass is a great tool to be able to run on the edge, runs on top of Debian, therefore runs on top of eLxr, so you can get it distributed. From us, run it on top of eLxr, and it manages workloads that are running. They can be data processing, they can be processes, but also they can be containers. So back to the types of tools that we want to use for development, here we go. This becomes the baseline for being able to work with distributed networks of cars and deploying models at scale. Certainly on top of this, we have to connect to something in the cloud. Cars don't necessarily talk directly to each other. I don't want to go out to every car to do an update. I have to talk to something in the cloud, and of course we have AWS IoT Core. AWS IoT Core pairs with services on AWS Greengrass, creates a secure channel for doing device management, for managing what workloads are available here through AWS Greengrass services. It opens up channels for being able to stream data. This gives me an entry point into the cloud to be able to use any backend service that I want. So I can still have a really flexible backend architecture. I can still have a really flexible containerized architecture on the edge using Docker networking, configuring everything just as if I was building a cloud service. This feels just like I'm building a cloud service, but I'm actually building a robust service for doing a really modern deployment in a car. And then the cool piece of this too is because we have this operating system that's tuned for the edge, very often what's running on the edge are ARM systems. Well, Amazon has ARM-based hardware in the cloud. I can click a button, I can fire up an AWS Graviton instance, I can deploy the same operating system that I'm going to deploy on the edge up on that VM. This will be coming to the AWS Marketplace later this month. We're already in the AWS Marketplace now if you want to go check out eLxr for x86-64, but it'll be coming in for ARM Graviton support. And this is really the kicker for saving money to me. When I work with customers, sometimes test beds for these types of products are extremely expensive. In the automotive space, yeah, sometimes there's some smaller boards that we can test on that are cheaper. When we start talking aerospace and defense, there's only one James Webb telescope. It gets really expensive. So for me, being able to test in the cloud, hugely valuable. I can have a full CI/CD system that does automated builds, automated testing, and have good confidence that my binary that was compiled for the edge runs in the cloud. I can run my tests. And so we're going to see a lot of that today. This is the overall stack. Really excited about it. Before I pass this over to Stefano, I just want to say Wind River has a booth here. We'll be at the AWS Pavilion if you have any questions. I know we can't take questions here. So please come over. It's booth 488 down, like I said, in the Industries Pavilion. I'll be there most of the week along with my team. Lexi will be there. So if you have any questions about this architecture, please come by. But really excited about this. It's saving a lot of time for us and really helping customers move forward at a much more rapid rate. So certainly excited about it. But I'll hand it over to Stefano. Thanks.
Awesome. Thanks, Joey, and thanks, Nikit. I think you already got an idea more or less in how the pieces are falling in place, right? IoT, we started with IoT connected, objects are connected. But in automotive, and very specifically in automotive, we are inside already a revolution that is software defined, right? A revolution that requires consolidation, as Joy described, because otherwise it's impossible to make the vehicle software defined. If you have all these ECUs, all these networks, all this complexity at an architectural level from the electronic perspective. So consolidation is making it happen. Software-defined vehicle is coming, but the elements that Joy were describing about having something in the cloud that represent the target operating system is super relevant. Think about if we add to this complexity of the transformation of the automotive sector to be software-defined, the complexity of managing large language models, small language model at the edge. It's another layer of complexity that is already on top of something that is very complex, right? So software-defined and Gen AI LLMs needs to go together. It's necessary because otherwise you won't be able to manage the complexity that is really entering when you start to deploy these technologies at the edge. And this is something we did and we experimented with. It was very important experience for us in the past 3 months where we put together this demo and experimentation. This is just, again, a specialization for automotive of what Nikit presented at the beginning of the presentation. So we are going from software-defined to AI-defined vehicles. And really applying this cloud-to-edge LLM orchestration really enables this fast and scalable solution for the automotive industry. This is really important, and I tell you that in the past 6 to 8 months, there is no customer conversation that doesn't have this as one of the, let's say, things that are in the agenda. So every major OEM tier 1 is looking at how to incorporate this kind of technology inside the cars, inside vehicles in general. Exactly for the reasons that Nikit presented at the beginning, real-time decision-making, privacy, reduced latency, and maybe reduce the dependency on connectivity, optimize the resource usage, more customization, local customization, the effect of the big loop in this sense, scalability, and so on, right? So this is really, really important. So I just want to remember, right? So when I talk about SDV, typically I describe 3 steps. So let me go through that a bit, because again, you will see how this builds on top of these 3 steps in a way. So the first step that is really important, and as AWS, we invested at least the past 3-4 years in this virtualization step. Because really, what Joy presented at the end, right, the fact that you can run an operating system on top of Graviton, right, an embedded operating system on top of Graviton, is enabled by, and let's say the market is really adopting it broadly, right, because we were able to kind of define and understand how to virtualize each of the domain of the car into cloud virtual electronic control units, right? So if you look at this, I don't want to enter too much into the details, but if you have an infotainment, most probably infotainment system, most probably is ARM64 with an hypervisor on top of it, can be, for example, Android, QNX, VxWorks, or other operating system as safety for the instrument cluster. This can be natively executed in cloud for most of the part, from the hypervisor up. So, and we assessed that, for example, through our partners of Qt, 90% of the development and testing process for an infotainment system can be done in cloud. First, without any kind of hardware that, especially in the first phase of the development and testing process. Does it mean that we eliminate hardware? No. It means that in a software-defined perspective, software comes first, and cloud-native software comes first. Then hardware is tested at the end of the process, because if you are dependent from the hardware availability, as Joy was explaining, at the beginning of the process, you are done, because you can't scale, you can't test. Cars still nowadays on old architecture are extremely poor tested objects. Think about that the system, given the complexity that Joy was explaining at the beginning. Current cars, they have a system coverage of approximately 20%. It's just crazy, right? So you can't really test deep, and the biggest reason for that is 2. Hardware availability, complexity of the electronic architecture, and the related verification and validation procedures, right? There's a huge bottleneck in the process. When all the suppliers are sending in the ECUs, they connect it on a table, and then they start to test it. But the number of variants, it's just exponential. So you can't really achieve a very good coverage if you don't make this simplification. Next is, so infotainment, I explain it to all the customers, we consider it a problem solved. Technically, it's a problem solved. So if you want to go through virtualization of this kind of system in a car, there are no technical limitations to do that. You gotta work with your supply chain, you gotta work with your internal team and organization to make it happen. Those are real problems, but technically we consider it a problem solved. ADAS, it's a little bit more complicated. We know how to do it. The problem is, and you will see, this is a problem that we highlighted as well for LLMs at the edge, the dependency on specific hardware for inference at the edge. Because you have NVIDIA, you have Qualcomm, you have other vendors that are providing this inference engine as a SoC, as an ASIC, so as a physical hardware. And the execution of the models on top of it is very dependent on the specific libraries and the hardware that you're going to use. CUDA for NVIDIA, ONX for Qualcomm, and so on. And the optimization that is coming from the model itself when trained depends as well on the hardware that you use for training and inference. So it's a very hard, and the thing is, you can't virtualize this kind of accelerators. It doesn't make sense to, of course, create a soft NPU or a soft GPU. It doesn't make sense. It's too slow. So the execution of the processes in cloud won't be efficient. A solution we found, and here you see, for example, the DL2Q instance in there, is to put, for example, in the case of Qualcomm, the Qualcomm AI100 chips and solutions in cloud as hardware, right, integrated in this kind of instances. In this way, if you are working with Qualcomm technologies, you can execute inference on the same hardware in cloud and the embedded edge. Okay. So we found a way to manage this, and there will be more coming at CES this year. Then, of course, even in the ADAS case, our customers tell us that approximately 70–75% of the process can be done in cloud first, without the need to have hardware except in the latest part of the process. Then there's a third case. Third case is, okay, here the first two cases, I'm just having more or less, I work with, let's say, instruction set parity, as we call it, so ARM64 in the car and ARM64 in cloud. But sometimes you want to have more fidelity. So here, for example, we model a case of a specific SoC that is an NXP IMX8 that you will see later on in the demo. And that is modeled in all the components with high fidelity, through proper partner technology, in this case, ARM virtual hardware through the Corellium platform. So this really is a high fidelity emulation of the final device with high performance, because anyway, it's ARM on ARM. So it's not just that we know how to do it. We know how to do it in a very efficient way. And just to give you an idea, this virtual IMX8 running on AWS cloud is going 7 times faster than the real IMX8. And this is not the same, always the same for this kind of emulation technologies, right? Traditional emulation technologies. Because it's ARM on ARM. So that's induce optimizations that are really in favor of better performances. The last case is when you have, again, an unsupported instruction set that we need to emulate completely on AWS. For example, if you have system powertrain based on Infineon or a Renesas or other kind of technology, we don't have those chips in cloud, so we need to fully emulate them. And in that case, we go through partner technology like Synopsys VDK, Synopsys Silver, ASTC VLabs, and much more. Okay. But again, the point here is we know how to virtualize almost all the parts of a car electronic system, including the networking. Because now it's not just a single ECU. The first time we presented this to customers saying, yeah, okay, nice school case, but I have more than one ECU. Can we model a domain? For example, infotainment, gateway, and telematic unit? Yes, we can. So we really created this kind of networking in our data centers, including distributed networking, that is really an innovative part. Not interesting for today, but of course I'm available after for questions or go deep on this element. So virtualization is really the first step. And again, virtualization first. You should always start, there's an order I'm saying. You should always start from the left and go to the right. Because, and you will see, this is exactly what we did in the demo that we implemented. Because on the left, you have more performance, less cost. And the more you go on the right, you kind of decrease the performance and increase the cost because you need other tools. It's not just a native execution of an OS as an Amazon machine image on AWS. The second step is really to put this together with the wide number of the large number of tools and other things that tools that the OEMs use on a daily basis, right? So, for example, here you see our virtual engineering workbench that is a platform engineering tool that puts together a target that is Android Automotive OS, and 3 tools. One is Atlassian Confluence for requirements management, Qt Studio as an IDE for the user interface, and Vector Canoe for testing. This is a classical configuration in an OEM. An OEM doesn't need, okay, a tool and what I do with it. I have a workflow, right? I have a complete workflow of operations to do, from requirements to V&V, and this is mandated for me to guarantee adherence to the regulations, as Joy was explaining. And here, this is just an example. There are multiple platforms, multiple platform engineering tools, and Wind River has a very good one called Wind River Studio, by the way. So definitely look at it. This is a super important step because it's not just a way to organize things, but to organize things in a cloud-native way. And this is super important because, believe it or not, some of these tools, they are super old. Monolithic exe files on Windows machines with no separation between presentation, logic, data, anything, and absolutely no APIs. This is a first step 0 to have these tools, to have at least a bare minimum set of APIs in order to be launched, managed, closed, in order to be integrated inside workflows, right? And this is another part that is super important. I have to say that after this effort, especially in this year, in 2024, we saw more and more tool vendors starting to deconstruct, to modernize their tools architecture, introducing more and more APIs and more modularity in the tools. And that's very important for the industry. Otherwise, you understand, if we want to have efficient processes, we will always depend by this lowest tool in terms of performance. And that's no good. The third step is when everything is organized this way, so you have virtualized targets, you have a proper platform engineering approach, and that means you have everything managed in a cloud-native way, both targets and tools. Yes, we can have finally the first big impact of Gen AI, and we call that AI accelerators for function engineering and development and testing, right? So this is in support of engineering. And if you want to know more about it, you can go to the session AUT310 tomorrow and Thursday, Wednesday and Thursday, where my colleagues Matt Pollock and Patrick Barsh are going to give an example of this process. You see the V model there, and you see how through these accelerators, we are really able to speed up the transition between the phases. Think about that the developer in automotive develops for 20% of the time. 80% of the time is transitioning. I didn't understand the requirement. Can you please explain it to me better? Or where is the source code here? I can't find the repository. Where inside the repository is the code I need to work with, right? So this is a huge, huge loss of time where Gen AI really helps. And we have an example, a demo related to this, where we were able to go from a process that from requirements management to verification and validation of a feature for a UI, for a Qt UI in 4 hours, instead of weeks that typically the sector took. It's not just us, of course, this is an internal experiment, but our customer BMW that is adopting part of it at scale, especially on the virtualization side, sees similar results. And then the 4 steps, that is really what we are presenting today. So 3 steps plus 1, because we can't just stop at the 3rd step. The 4th step, natural, is how you manage the orchestration of agents, of AI agents from cloud to edge. When you have this architecture, the tools to validate, the virtualized targets, the connectivity that brings up the data, brings down the software in the big loop perspective that Nikki was referring to, the next step is orchestrating this AI agent. That go and help everything else. Think about how you can improve the software of the car, how this is tightly related to this kind of 4-dimension, 4 steps. And here we just generated this architecture that, in my opinion, it's kind of cool. It's the first time we're presenting it. So a cloud-to-vehicle edge LLM orchestration, where we have the first element that happens in cloud, where you have, again, your virtual target, Amazon SageMaker to customize the model, and then a first step of testing through the ARM virtual hardware, emulating an IMX8 Plus in cloud, so a fully virtualized target, fully emulated target, high performance, and then the real hardware. And this is really, I think, a very modern approach to have software-defined and AI-defined vehicle development. So first is the cloud-to-edge orchestration, and facilitated, of course, by the use of eLxr. And think about how Aptiv and Wind River have been innovative in starting this embedded project, not just on a physical hardware, but as a cloud-first element. I think it's the first time, it's one of the first time of the market where a new initiative on a new embedded operating system is presented as a cloud-first option. Saying, start with the cloud with my embedded system. Later on, where you'll think where to port in your hardware elements. And this is disruptive. This is what we should do in every new project in automotive. Second is this staged SDV development. You will see about that. Automatic model updates and IoT integration and analytics. Those are not accessory. Those are absolutely necessary functionalities, and I'll explain you why. Of course, first step, the order is super important. The first step is totally cloud first. Here we're going to use, again, an AMI with eLxr on top of it. On top of eLxr, we have our small language model and the application. The application is a user manual for a car. So you want to ask information related to what's happening in the car. Maybe you have a telltale going on, something going on in the instrument cluster, you don't know what it is. Happens to me all the time. I don't know about you, but even if I'm an automotive nerd, it happens to me all the time. And I think, oh, what is this thing that I'm seeing on the instrument cluster? Oh yeah, that's the oil pressure for this kind of subsystem. Do I need to stop the car immediately? No, you can just go ahead. But this is a kind of a delicate conversation to have with my car, right? My car is suggesting if I can stop my car, I need to bring it to the maintenance. This is probably something that is a little bit safety related. What if the AI is saying that I don't need to stop the car, but I need it to? And so my car, maybe the engine is just burning or whatever, right? So very important element to be considered. Some of these LLMs application at the edge are critical. So the same way we require mixed critical orchestration for functionalities, we require a little bit of mixed critical orchestration for SLMs, for language models at the edge. Super important. This is one of the first learning we got. Then you see how this, we have SageMaker there. What we did was to do a tuning of the model, a specialization as it's called technically. So we didn't trade a model from scratch. We took a tiny ML model, and then we specialized it in order to learn the user guide, the specific user guide, car manual of the car that we were targeting in the demo. So all these operations are done already on eLxr, on the target operating system. This is, you realize how big is the shift left here? We are starting immediately with the final target operating system. This is at least, I don't know how many months and how much scalability you can achieve. Because before, you could just do it on an evaluation kit, on a real hardware, but how many can you have? And how much they are available? Joy presented it nicely before, right? And then this is really important, right? So start this way, agile, maximum level of abstraction. You can iterate fast, you can share it with colleagues in a click. You can share the AMI all around the globe, because of course we have global presence as AWS. So maybe you wanna have a colleague in Japan to test it, to provide feedback. You can do it super fast and at a very high large scale. This is exactly what you want, because here you don't have a system integrator or a V&V person that is doing this job. Here you have an LLM developer that develops the application. So why you want to bound them to a specific hardware, to specific hardware requirement? There's no need for that in this phase. That will come later. Okay, the persona is really relevant when targeting this kind of SDV steps. The second is, okay, now we reached a certain level of maturity. So let's go to the next step and introduce the ARM virtual hardware. Okay, ARM virtual hardware in this case is an NXP IMX8 Plus, where I just deploy the same components and run them on top of eLxr running on the ARM virtual hardware. So it was insane in this experiment we did. We took less than 2 weeks to bring eLxr from the physical IMX8 to the virtual one. So it was a super fast operation. Development time, I think it was even less, 2 weeks overall as the start when we had the idea, but it was even less, right? To tell you how much a virtual IMX8 is functionally accurate with the physical one, okay? So why we are doing that? Because here we can start to integrate, to do system integration testing. So it's not just anymore the performance in terms of application of the Gen AI part, but is this interfering with the processes, with other applications I have on the target? How that interacts with the Cortex-M that I have there as a safety island? Because IMX8 is a Cortex-A plus Cortex-M. Cortex-M is the safety island. So I can study more dynamics. And again, shift left all that part of testing way before the hardware is even available, okay? Third step, real hardware, right? So, and here, what we do here, we test the physical characteristics of the system. That means the performance at the very end. That's at the very end the only thing that really matters, right? And the thing is, another thing that we understood very well is it doesn't really matter to achieve the same level of performance in cloud and the embedded edge. It's very important to set a performance bar, right? Is it the representation in cloud good enough to represent the physical performance? Yes, no. Because from this perspective, if a conversation happens in the 350 milliseconds or 400 milliseconds, who cares? The user won't notice it. It's good enough, right? And this is super important because, again, it's a simplification of the entire workflow and process. Last step, collect, finally, we have the driver in the loop. And we collected the usage of the driver, what the driver is doing and asking to the SLM. This is super important because, of course, you can train up until you want, but believe me, you will always have surprises when you put this out. So you need to maybe collect a weird answer, a weird question that you didn't consider before. And this has to go in a dashboard that presents this kind of weird questions. And the user satisfaction even more. So demo time. It will be a set of screens, but we have the video. So if you are interested, we can show you the real demo in a bit. First step is going to SageMaker Studio, as you can see, and specialize the model. We start with Tiny Llama and 3.6 gigabyte of a model. So you can imagine, of course, we needed to optimize, quantize it, and transform in a 600 megabytes, more or less, packet to download into the car. The second step is provide the training material to specialize Tiny Llama. And this is all the Excel file that we created with question answer. That's the way you do the specialization of the model, okay? The third step is, okay, now we specialize the model, we have the model available, we put it in S3, ready for deployment. And the deployment starts on eLxr. You see here how easy it is to access this embedded operating system, eLxr, on our AWS marketplace. It's a matter of subscribing to it and launch it as a regular AMI, as you do with any kind of AMI that you use in AWS. Through console, through CLI, through SDK, whatever. It's just an AMI, another AMI. You launch it on eLxr, and here you see the result. Again, LLM chat. So you see from uname-a that is eLxr Linux running natively on AWS. And then you launch the chat server in a way with the specific bin, the quantized model obtained by the Tiny Llama. And then you can start the chat. So how do I respond in car's engine indicator, lights turn on? This means there is an issue with your engine. Please check this issue with an authorized dealer. Okay, this is kind of an example. The performances here in terms of question answer are sub-second. Okay, so we already achieve good performance in the way this is exercised as an AMI. Good, next step, let's launch it an ARM virtual hardware. So this is the way it looks. So it's AWS app avh-corellium.com, ARM virtual hardware, where you can launch virtual boards, leveraging ARM on ARM. All of this run on AWS Graviton for a reason, because all these systems are ARM. ARM64 on ARM64, super good performances. And this is how it looks. Same thing as you saw before. You have a virtual desktop, virtual desktop from the IMX8. And then same thing, right? So you launch the client in this case, and you can start to chat with the bot. eLxr on top of it, same exact thing, right? But now we are not anymore on an ARM64. We are running on a Cortex A53. That is the processor, the specific CPU that the IMX8 is using. So we achieve a level more of fidelity. Performance is the case, sub-second as well. So we didn't notice any variation in terms of performance. Third step is bring us components. Now we want to deploy on the real hardware. We have the S3 model, and we want to use Greengrass to deploy as in a real case, right? And here you have a deployment group, and then you deploy it on the physical hardware, and the physical hardware that is a physical IMX8, so a real board, with a eLxr on top of it. Performance is here, 6-7 seconds, right? That was surprising to see, again, the virtual board, but it's exactly as I was saying before. The virtual board is going 7 times faster than the physical one. So 1 second, 6-7 seconds to get an answer in the specific case. Why? Because one of the issues, as I told you, is heterogeneous hardware to execute inference. In cloud, we have Graviton Neoverse, ARM IP. Here, in this case, we have an NPU, and the Tiny Llama is trained on a CUDA, on an NVIDIA system. The NPU on the IMX8 is not optimized to run that specific model. And so this is what we achieve. So this is something, still a friction that we are working on the sector. So key takeaways in a minute. LLM market is growing super rapidly. Edge processing offers benefits, but it was an interesting set of lessons for us. Human supervision is necessary and very strong guardrails, especially if we are dealing with sensitive cases. Performance assessment and management is super important. Where possible, simplify setting performance bars. It's not necessary to achieve high fidelity at all costs. Heterogeneity in the training inference execution across different vendors is an issue that we need to work as an industry. And there's Ed from ARM in the audience. It's something that, for example, with ARM, we are pretty much looking at. They introduced this Clady AI library that hopefully will simplify part of it, but still we need to work on that. AWS provides solutions, obviously, for that. And again, it's these 4 steps are really important: virtualization, platform engineering, and then cloud to vehicle orchestration. And at the end, on top of it, when everything is cloud native, put your LLM, SLM orchestration from cloud to edge. eLxr has been a fantastic approach. Again, I think it's really an innovative approach to introduce this kind of operating system this way, with this SDV staged approach. That, in my opinion, is really the way all new projects in automotive should start. So, me, Nikit, and Joy will be available here. If you have any question, we'll just hang up for a bit. Thank you.